Welcome to Derivability. Let's take another look at Snell's law. Recently I made a video about Snell's law using wave properties. Okay, this time let's just completely ignore the fact that light is a wave, or whatever it is we're talking about is a wave, and let's use something called Fermat's principle of least time. Okay. Now, what we're going to do here is we have a refraction scenario, if you like. Okay, we have a dot in the upper left of our picture. That's the starting point, maybe the source of light. Okay, it shines a beam in some direction. What we want to do is we want to get that beam from start to finish. Okay, from this starting dot over here to this ending dot, and let's suppose we want to do it in least amount of time. Okay, now at this stage, we just have no idea how this is going to turn out, but I like to compare this to like a good old Calc 1 problem that you may have seen in a Calculus 1 course. I like to call it the lifeguard problem, where you have say a lifeguard over here, and maybe somebody who needs help over here, and the lifeguard needs to get from his position to the person who needs help in the least amount of time. Okay, and maybe he's running on pavement, like along path D1, and then maybe along sand on D2, where you have different speeds, V1 and V2. Okay. Now, most lifeguards don't study this, but if they did, they would be well advised to think about Fermat's principle of least time. Okay. Now, again, our context is the path of light, and we're going to see what path the light or the lifeguard would have to take in order to get between these 2 points in the least amount of time. Okay, so the blue rays are the paths of light. Okay, distance d1, traveling at velocity v1. Okay, likewise d2, v2. Okay, and in the spirit of the fact that we're thinking about light, then we want to measure the angles relative to the normal. Okay, theta 1, theta 2. Okay, let's suppose the horizontal distance between these 2 points is L. Okay, labeled up at the top here. Okay, and we want the lifeguard, or rather our light beam, to cross between the two media at some distance x measured from the left. That means we have a leftover L minus x on the right side of that boundary. And vertical dimension h1 and h2, as you can see. Okay, so to set up least time, what we're going to have to do is set up maybe the total time as a function of x. That seems to be a handy variable here. And then we want to minimize that as a function of x. So let's start here in a minute and we'll see how that goes. Okay, so let me use capital T to stand for the total time. Okay, that's going to be the sum of the individual times. Okay, so if you like, time 1 along path 1, that's going to be d1 over v1, and time 2 along path 2, that's d2 over v2. Okay, now let's express each of these diagonal distances using the Pythagorean theorem. Okay, so you can see here that d1 is the square root of h1 squared plus x1, and then likewise we have this other square root, the Pythagorean theorem for d2. Okay, now what we want to do next is to find a minimum value for time. We want to take the derivative of capital T with respect to x and set that equal to 0. Okay, then the normal procedure is to solve for x, find the x that corresponds to the minimum time, and then plug that into our original formula for time and see what the minimum time is. It's not exactly how we're going to do it here, but the first several steps will remind you of the familiar calculus procedure. Okay, so let's take the derivative of our expression with respect to x now. All right, so let's take a look at that down at the bottom since that turned out to be kind of a long equation. Okay, but the idea is that the square roots that we see up here in the original equation for time right here, okay, the square roots are really 1/2 powers. Okay, so the velocities are in the denominator, they're constants, so we get the 1/2 powers coming down with a negative 1/2. Okay, and then chain rule says we have to take the derivative of the insides of each of those expressions. Okay, so the derivative of x squared with respect to x is 2x. Okay, so we get a similar maneuver here with the 1/2 coming down, negative 1/2 power. Okay, and then we want to take the derivative of the insides with respect to x. Okay, so we get for the second term, that chain rule is going to give us 2 times the grouping L minus x. And then x it has a negative 1 coefficient right there, so that chain rule negative 1 comes out. Okay, so before we go to the next step, we're going to see a lot of things happen here that are kind of nice. So we get a 2 and a 1/2 canceling in a couple of different places. All right, and what I have in mind is to take this second term here, and since it has a kind of a net negative, put that over on the right side of the equation where it's going to become positive. And then maybe we can rewrite those negative 1/2 powers as square roots in the denominator in our next step. Okay, so we got things back up at the top there. Okay, so the 1 over v1 and 1 over v2 parts of each term, they just remain. Okay, and then there's an x and an L minus x that remain up here. Okay, and then each of these negative 1/2 powers, okay, the 1/2 power can be written as a square root, and the negative means it goes in the denominator. Okay. All right, so let's kind of take account of what's happening. Let's express things maybe back in terms of the distance. Okay, so again, this square root, that is d1. This square root is d2. Okay, so let's just go ahead now and replace each of those roots with the d1 and d2. Okay, so there we go. All right, now I don't know that we really needed to do this step, but I think it's just a little easier to see what's going on when we do that. Okay, so x over d1. Okay, we're taking the ratio of these two sides of that triangle. Okay, now angle theta 1 lives right there. So if you take a careful look at this right triangle, x over d1 is really the sine of theta 1. Okay, and L minus x divided by d2 likewise is going to be the sine of theta 2. Okay, all right, so let's clean that up. All right, so we've written that in terms of the sines. Now, if you have seen another approach to Snell's law, you almost certainly see where this is going. All right, but let's just finish this off now. Okay, what I want to do next is multiply both sides by c. Okay, I'm going to think of these as c over v. Okay, and c over v is the index of refraction. So finally I can write that equation with the indices of refraction with the signs. So there we go. Okay, so we have arrived at Snell's law here without having to assume that there are any wave properties at all going on. Okay, so do things obey Snell's law because there's a wave property happening, or do they obey Snell's law because of a least time principle? Okay, now it may be deeper than either one of those. Okay, but Fermat, I believe, just wanted to show that there was an alternate approach that could explain the same thing. And like I was saying at the beginning of the video, our so-called lifeguard problem obeys Snell's law. Okay, and I don't believe that there, there's anything intrinsically wave-like about the lifeguard running from his starting position to the position of the person needing help. Okay, of course, in quantum physics, matter has wave properties, but I don't think that really is a practical effect here. All right, well, thanks for hanging around till the end of the video here. I enjoy doing these. I hope you enjoy them too. So please give me a share, a like, subscribe, leave some comments for me, maybe with some suggestions for videos to do in the future. All right, so thanks for dropping in, and hope you enjoyed it. We'll see you again soon.